Chapter 1, slides 1 through 9. What is organic chemistry? So as we begin this class together, I wanted to discuss a little bit of history about organic chemistry, where the term comes from, and a little bit about how it's changed over time. Right? So back, which isn't, in the grand scheme of time, not that long ago, 1807, the two kinds of materials were given names, organic and inorganic. And these compounds were defined according to where they came from. So if a compound came from a living organism, it was believed to have some sort of vital force. And so they called these compounds organic. Compounds that came from minerals or those that lacked a vital force were called inorganic. And these two terms are still used today, but they don't have the same meaning as they did back in 1807. And one of the things that was a game changer was Frederick Wohler in 1828. He ended up synthesizing effectively urea, right, which is a compound that is excreted by mammals. And he did it in the lab. And so technically he himself made something, without having excreted it from a living organism that typically came from a living organism. So this is where the whole terminology really shifted. So nowadays, organic compounds are defined as compounds that have carbon. So if you're looking at a molecule and it has a carbon in it, it is an organic molecule. Doesn't necessarily have to have come from a living organism. And we now have an entire branch of chemistry devoted to studying carbon-based or carbon-containing compounds. And depending upon where those carbon compounds are found or made from, it defines the type of chemist that you are. So proteins, enzymes, vitamins, lipids, carbohydrates, nucleic acids, you all take biochemistry courses, understand a lot of the macromolecular structures in our bodies. These are all carbon-containing molecules. Other things like food, right? Medicine, clothing, right? Cotton, wool, silk, all of these have carbon-based structures. Energy, natural gas, we can think about propane and butane and octane. Coal, these two are carbon-based molecules. But what's interesting is that there's over 16 million synthetic materials that are not found in nature whatsoever that are also, according to the definition now, organic molecules. Synthetic fabrics, plastics, rubber, medicines. So really, what this course is all about is understanding molecules that contain carbon. We do have other classes dedicated to the other side of the periodic table, inorganic chemistry, the ones that sometimes contain carbon still. We have organometallic molecules. We also have molecules that do not contain any carbon and may have metals only. Here's some examples of some organic molecules that come from nature, like penicillin, vitamin C, codeine. Taxol's a large molecule extracted from the Pacific yew tree, the bark, and it's used in cancer treatment. But there's also a lot of organic molecules that are not perhaps as helpful as the ones I just showed. Just because something comes from nature and is organic, right? We're not talking about the organic in the vegetable aisle at the grocery store. We're talking about our definition of carbon-bearing molecules. And there's plenty of carbon-bearing molecules that you would not want to ingest simply by the fact that it is quote-unquote natural. An example being belladonna, strychnine, and aconite, right? These three are very poisonous plants, and they are organic-based compounds that will kill you. So just because something is natural does not mean that and organic does not mean that it's good for you necessarily, right? And so it's very important to really truly understand the difference or lack thereof between natural versus man-made or synthetic. Again, strychnine is natural, but I'm not going to ingest it. So structure and function are really important, right? What effect it has, what the structure is, how we define that structure. And we're going to learn a lot about that in this course. But it's a nice takeaway as a citizen of, the world to understand the difference and to not be afraid of the word synthetic. Carbon on the periodic table is carbon. Hydrogen is hydrogen. If nature makes a bond between carbon and hydrogen, and I do the exact same thing in a lab, take carbon and hydrogen and put it together, it is the same molecule, right? If I follow we're both following the same blueprint and our building blocks are the elements, and I put things together in the exact same way that someone else or something else puts it together, it's going to be the same molecule. Carbon on Saturn is carbon on Earth. And so these building blocks, as long as we follow the same protocols, man-made versus natural really doesn't matter. The trick of it is that natural, when molecules come from a natural source, it tends to be harder to separate, right? The molecule's in there, it's probably in very small quantities because it's an amalgam of so many different other things. And so isolating it and purifying it away from all the other things that organism is making and brewing can be more challenging than actually going into the lab and only adding the things that you need to make the molecule of interest. So sometimes synthetic can be more efficient and faster and a little purer because you don't have all of the other side stuff that the natural compound might be making. So at the end of the day, I hope that this course will allow you to become a better educated citizen, since we all have bodies that are full of organic molecules, right? We're all living organisms. It's part of our hair, our skin, our muscles, genes, DNA, everything that is us. It's also in the food we eat, right? And the medicines we might take, or the materials we are consumers of. So I think having a basic understanding of organic science is really important just to our everyday lives. And it's also hoping that we can all build a really strong foundation so that as you take upper level courses that deal with molecules, that deal with molecular structure, this course will help you in understanding bond theory and functional groups in order to have hypotheses about what's going on, why the phenomenon you're studying in some other class is actually happening, and taking it all the way back to the molecular level, which this class will allow you to do. It is foundational, and I relate it to others. You would never expect to take a calculus class if you didn't understand how to add, subtract, multiply, and divide. It's foundational to building that more advanced knowledge. And to me, organic chemistry is the addition, subtraction, multiplication, and division for the other courses you might take. Without it, you might have to memorize a lot, or you might struggle to understand the whys. You might have to collaborate with more organic chemists in order to understand it. But you'd be surprised how quickly and efficiently just a simple Orgo 1 and Orgo 2 class can make you into that scientist, right? That informed person in the lab. For this course, I'm going to be using words like retrieval cues, and these are basically important concepts that you really have to understand in order to appreciate and move forward with the material. Please retrieve is just my way of saying, we've studied this already in this class, and if you still don't get it, go back and remember how to do this. It's just like buff up on this concept in order to move forward on the new one. Most importantly is critical skills, and I will put this term wherever I need you to practice something. It's where it's something that I need you to get a lot of practice honing your skills at so you can master that problem-solving requirement, or to understand how to use or how to apply a retrieval cue concept. So whenever you see critical skills, you need to get a lot of practice. And if you're really struggling at a critical skill, that's when you need to ask for help. So let's get started. what happens to a molecule during a reaction? If this could be sort of the tagline for this course, we're going to be spending a good chunk of the beginning of this semester really getting you up to speed with terminology and basic concepts and three-dimensional structure and bonding. It'll be late in the semester when we actually can start looking at reactions. We really have to understand a lot in order to get to reactions. And so this is really the summation of the course. What's happening to molecules during reaction? What's happening to carbon-based molecules during a reaction? So we're going to be looking at collisions of molecules and the effect of bond making and bond breaking when these collisions occur. So one of the big questions that we'll ultimately get to, but we'll need lots of time in order to do this, is how and why this happens. The big one being why. Why do these reactions occur? And how can we make predictions upon whether they are going to occur and what they're going to look like on the other end of the reaction arrow? And to do this, our entire class is going to focus on electrons. So in order to do that, we've really got to start at the basics, right? At the atomic theory. So that's where this chapter begins. And a lot of this is review, but you'll see that it's review of your general chemistry knowledge in a very qualitative way, not a quantitative way. We're not going to be doing a lot. You're not going to need your calculator. You're not going to be manipulating numbers very often, if at all. We're going to be looking at a very qualitative way of focusing on electrons and making hypotheses as to their behaviors. And so here's a question that I'm going to end the chapter with. We see it how I'm posing it to you now, and I'm starting with a very simplistic reaction that you may be familiar with. Notice that it is not an organic reaction. It doesn't have any molecule containing carbon, but these are molecules that you worked with in general chemistry quite often. So I'm just going to draw them out using their bonds in Lewis dot structure. And we have hydrochloric acid and sodium hydroxide. And you might, for whatever reason, maybe you've seen this reaction a dozen times and you're like, yeah, I know, it forms NaCl and water. And maybe you've calculated lots of different things a bunch of times for this reaction. But what we're going to do in this course is really look at the bonds that the starting materials have, the functionality of the bonding systems, and how to predict what's happening for the bonds. Like basically we're looking at the arrow, right? I'm interested in this arrow. What's happening as this transition is occurring, as bonds are being broken and bonds are being formed, and why the products may or may not be favored. Okay, so to work on this reaction above, we need to understand bonds. And to understand bonds, we need to understand atoms. And to understand atoms, we need to understand protons and electrons and neutrons and the atomic structure. So I'm backing up. We're going to do a lot of review in this chapter, and we're going to build our way up to being able to talk about bonds by the end of the chapter.